Welcome. Today we're going to talk about Unit 7.4, solving exponential and logarithmic equations. By the end of this lesson, it's my hope that you will be able to use properties of exponents and logarithms to solve these types of equations. The first property we're going to look at is the property of equality for exponential functions. And what this says is that if you have a base greater than 0 and not equal to 1, then b of x is equal to b of y if and only if x equals y. As you've heard me say in the past, that's all mumbo jumbo. Let's look at a real example. What this property really means is that if you have something like 3 to the x equals 3 to the 5th, then x equals 5. Conversely, you could say if x equals 5, then 3 to the x equals 3 to the 5th. It goes both ways. We can actually use that property to help us solve some exponential equations. Let's try one. I have some steps written out. It's handy to have these around so that you can make sure that you're following all the different rules. The very first rule is, or step, is to figure out what the common base is between the two components of your equation. Clearly the base here is 2, the base here is 8, and they are not the same. But I do know that 8 can be rewritten using base 2. So if I think about 8, that's really 2 times 2 times 2, or that's 2 to the 3rd power. And all three of those notations are equivalent ways of writing the number 8. So what I can do is, instead of using an 8 here, I can substitute 2 to the 3rd power for that 8. They are equivalent. I still need this exponent. It's coincidental that these two exponents are the same. They may or may not be, depending on the one you have. But now I have rewritten my original equation, and I have a common base, which I need to have in order to use this property. The next thing I'm going to do is simplify my exponents. What does it mean to have 2 to the 3rd power to the 3rd power? Well, this is if it's a property of exponents that says when I'm raising a power to a power, I actually multiply the exponents. Still not changing the left-hand side of this equation, but this becomes 2 to the 9th power. And if you're not sure why that works today, go ahead and write out what it means to be 2 to the 3rd power, and then what it means to have 3 copies of 2 to the 3rd power. I think you'll see what it looks like. Finally, I used my property of equality to say that my exponents are congruent. So x is equal to 9. It's pretty handy, huh? Anything new like this takes practice, so let's do some. In example 1, I'm given 9 to the 2x minus 1 equals 3 to the 6x. Step 1 above suggests that we come up with a common base. The right-hand side of my equation has base 3, the left-hand side base 9. And I remember that I can write 9 as as using a 3 for an exponent. So if I remember, 9 is really just 3 squared. So I can substitute in 3 squared instead of using the 9, do a little mini brackets there, 3 squared. And now I have a common base. Step 2 from above tells me that I need to simplify, I lied, this is step 3. Step 3 says to simplify my exponents. And I need to do that by distributing this 2x minus 1 to the exponent here. Technically, it's probably not called distribution, but that's the way my brain thinks of it. So I'm going to do that now, and I'm going to multiply 2 times 2x minus 1 and raise my 3 to it. And then on this side, I still have 3 to the 6x. Okay, so now when I do that, because I have a common base, I can forget about the bases and just set the two exponents, I forgot a 2 in there, equal to each other. End up with 4x minus 1 equals 6x. And when I simplify that, pardon me, I took up too much room. I end up with -1 equals 2x, or x equals -1/2. That is the solution to that exponential equation. Let's try another one. Example 2. Step 1, identify the common base. In this case, the common base is going to be 4. I'm going to remember that 4 times 4 times 3. 4 times 4 is 16, times 4 again is 64. So 4 to the 3rd power is 64. So I'm going to rewrite this using a base of 4. I'm going to keep the other side of my equation the same. And because my bases are the same, and I have no exponents to simplify, I just set the exponents equal to each other. And when I do that, I end up with 2n minus 1 equals 3. Those are the exponents for my common bases. Solve this little puppy. I end up with 2n equals 4, n equals 2. Not so bad, I hope. I'm going to skip number 3 because it's very similar to the one we just did. And I'm going to move down and look at example 4. You can find example 3 completed in the online notes. If I look at example 4, the reason this one's just slightly different is that I don't have an immediate base that I can see. 9 and 27 are both powers of 3, though, so I can rewrite each side of this equation using base 3. So if I think of 9, we've already discussed this. This is 3 squared, and I know that 27 is equal to 3 to the 3rd power. So I'm going to use those as substitutes for 9 and 27. And I'm just going to go ahead and take the liberty of writing this one over here while I've got it. Once I have a common base, I need to remember to keep my original exponents. I like protecting my exponents. And now I have a common base. Step 3 says to simplify my exponents. And I am going to do that by just real quickly multiplying through by my exponent. 2 times 3 gives me 6x. 2 times 1 is 2. And on the other side of my equation, I have 3 times 3x, 9x. 3 times -1, -3. And now I have a very friendly equation that I can solve. I'm going to subtract 6x from both sides. And then I'm going to add 3 to both sides. And lastly, I'm going to divide by 3. I'm going to leave my answer as a fraction because fractions are friends, and I'm set. Let's look at example 6 next. This one might look intimidating because the base on the left-hand side of this equation is a fraction. But let's remember that our fractions can be rewritten using negative exponents. So if I think about this one, I will do that over here. 6 to the -1, because it's a negative exponent, I flip and become positive, is the same thing as 1 over 6. And 2 to the 216 can be rewritten as 6 to the 3rd power. Again, the table we had when we did our exponential unit that has all your squares and cubes can come in really handy right now. Okay, so what I've done is I've created a common base for 1/6 and 216. So I'm going to use that new base and substitute it in for my original base, keeping the original exponents. And there were no exponents over here, so that side is good to go. I do not need to distribute anything. My exponents are already simplified. So I'm just going to set my exponents equal to each other. And if I do this, I should end up subtracting, wrong color, subtracting 3 from both sides. Ah, I lied. I do need to distribute this. I didn't lie, I just forgot. There is a -1 there, making this a -x and this a -3. I caught myself just in time. So now I'm going to add 3 to both sides. I end up with -x equals 6, or x equals -6. And there we have solved a rather complicated exponential equation. One cool thing about understanding the property of equality for exponential equations is that it can help us solve logarithmic equations. Remember that I can take any exponential function and rewrite it as a logarithmic function and vice versa. So if I'm given a logarithmic equation to solve, I simply rewrite it as an exponential equation, write it using common bases, and then solve the way we just learned. Let's try that now. The first thing I need to do is write this as an exponential equation. I identify 2 as my base. In this case, my exponent, if I do my log roll, becomes 2x, and I know that this is all going to be equal to 16. I've done my log roll, and now I have an exponential equation that I can solve by finding common bases. Next, I need to remember that 2 can be rewritten using, 16 can be rewritten using a base of 2 by remembering that 2 to the 4th power is 16. So I'm going to rewrite this as 2 to the 4th power. I'm going to keep my left-hand side the same. And now, because I have a common base, I can set my exponents equal to each other. And now we have solved our first logarithmic equation. Let's try another one. Just make sure we can see this. Yes, we can. Okay, so for this one, I need to rewrite my logarithmic function as an exponential function. It has a base of 3. I do my log roll and identify 4 as my exponent, and I know that that is going to be equal to 2x plus 3. You might, at this point, ask yourself, Ms. Palmer, how can we use the property of equality? Well, notice here, folks, I don't have an exponent that is a variable. So I can just evaluate 3 to the 4th power, which is really just 81, and solve a simple 2-step equation. I'm going to subtract 3 from both sides, giving me 78 equals 2x. X equals 39. I knew that. Let's try example 7. I first need to write it as an exponential equation. X is my base. I'm going to do my log roll. My exponent becomes 3, and x to the 3rd power is going to be equal to 1,000. Again, referencing your chart that has your squares and cubes on it, you'll easily see that x is equal to 10. 10 times 10 is 100, times 10 is 1,000. All right, let's move on. Okay, so it turns out there's yet another property of equality, but this time for logarithmic functions. It's similar to the one for exponential functions in that it says that if b is a positive number other than 1, log base b of x equals log base b of y if and only if x is equal to y. In real terms, that means that if you take an example like log 5 of x equals log base 5 of 8, then x has to equal 8. and vice versa. We can use this to solve logarithmic equations that involve logs on both sides. We just need the base for the logs to be the same. So if I look at my original equation, the first thing I notice is they both have a base of 2. That allows me to use the property of equality for logarithmic functions. And this property tells me that whatever follows my log statement should be set equal to each other. So in this case, I'm going to say that x squared minus 4 is equal to 3x. Once I've done that, I've eliminated the log portion of the equation, and now I'm just left to solve a regular quadratic equation. Remember, when solving a quadratic equation, you need to move all your terms to one side and factor. When I'm factoring, I'm going to find factors of a times c, -4, that add up to -3, sorry. So factors of -4 that add up to -3, 1 and 4, that would add up to a +3, 1 and -4, 2 and 2. Those are the different combinations. 1 and -4 is the one I'm looking for. So I'm going to write this as x minus 4, x plus 1 equals 0. I'm going to set each term equal to 0. And I'm going to solve my baby equations. And I end up with x equals 4 and x equals -1. We've solved our equation. It looked really intimidating, but turned out to be no more difficult than solving a simple quadratic. I, however, need to check for extraneous solutions, and that can look a little strange. Because I have 2 solutions, I have to check both of them. I'm going to check the first one right here. And I'm not going to actually solve all the way down to decimal numbers. I'm just going to make sure that at the end, we're taking the log of the same thing. So if I look at this first one, I'm going to substitute 4 in for x, 4 squared minus 4. And I'm going to check to see, is that going to be equal to 3 times 4? 4 squared is 16 minus 4. 3 times 4 is 12. And when I check these, I'm really taking the log base 2 of 12 on both sides, so I know that works. I was just too lazy to write log base 2 in front of all of my statements. I have to also check for x equals -1, and I'll do that the same way. -1 squared minus 4. Is that going to evaluate to the same thing as 3 times -1? Negative times negative is positive. And I again end up with an equation that is equal, and therefore both of these solutions are real solutions. Let's practice a couple more, then I will leave you for the day. The next one I'm going to look at is log base 3 of 2x plus 3 equal to log base 3 of x plus 13. So first and most important thing, I notice that the bases are the same. That allows me to use my property of equality, which says that I can set 2x plus 3 equal to x plus 13. And this is a nice friendly function to solve. I'm going to subtract x from both sides. I'm going to subtract 3 from both sides. I end up with x equals 10. I suspect that if you haven't already, you're going to kind of like logs because this is pretty easy math. For example, 9, I'm going to check to make sure my bases are the same, and they are. So I can set 4x plus 5 equal to 2x minus 17 and zip through solving this equation, subtract 2x from both sides. Subtract 5 from both sides. And now finally divide by 2. And I will want to check both of these examples to make sure that my solutions are not extraneous. 10 times 2 is 20, plus 3 is 23. 10 plus 13 is 23. So I know that 10 is not an extraneous solution. And I can do the same thing here. Hope you enjoyed this lesson and look forward to hearing from you again soon.